I'm going to have to so unfortunately this is not going to be great. So I'm going to start recording this session. Start recording. So the camera is recording, but because I don't have another tripod, it has to sit on top of the box for the webcam, which means it's too close, so you're not going to be able to see all the board. Because so I will try to get somebody to set up Teams in such a way that I can record only what I'm saying. Fine. But today we're going to sort of finish off a bit more of NP completeness. I hope I'm going to get through most of it. So if you recall, and if you don't recall, then you can just go back and watch the video for lecture 13. If you recall, in lecture 13 we were discussing so clique and independent set and vertex cover, and we said, yeah, okay, obviously if you can, this is almost like if you come up with a polynomial time solution for any of them, then because you can convert each of them into the others in polynomial time, you get a polynomial time solution for all of them. So this is sort of like saying, if you can find, when we found a linear time algorithm for max sum subarray, we automatically got a linear time algorithm for max sum subarray in a circular array, right? That was why we were doing that, to sort of teach you that people actually do this kind of thing, this code reuse, this idea that if you have an algorithm for one problem, you can use it to solve other problems. Usually you use them to solve similar problems, but sometimes you can make problems turn into other problems in sneaky ways. Okay, so clique, independent set, vertex cover, that was pretty easy. And then we said, okay, there's, we could do clique into sat. That was not so easy, because it was easy to say that if you have this vertex in the clique and this vertex in the clique, then there better be an edge between them, because we just said for each pair of edges, for vertices which don't have edges between them, they're not both in the clique, right? So we just had a variable for each vertex saying whether or not it was in the clique, and then for each missing edge we just said not XA and XD. Okay? So we saw that we could use sat as sort of a language to express other problems. We could take what looks like, what is a graph problem, clique, and we can write a formula that says this graph has a clique of size k. The tricky part was saying of size at least k. The tricky part, well, or exactly k, because if it has at least size k, then it has one of size k. The tricky part was saying this k stuff, because there, if we just go through and say so one of these subsets of vertices of size k is in there, that took too long, so we had to do that dynamic programming style table, which, don't worry, I wrote it up and sent it to the scribes, so there'll be a nice version in the scribe notes. And then we did this Satan transformation, which showed that you can reduce. So from sat, given a Boolean formula, you can sort of write it as a circuit, and then for each gate you can sort of, you assign a variable to the output wire, and you write a little formula that says the output is true if and only if it should be. Right, so and then we took this, so that way we could turn sat into 3 sat. So we had this thing where clique could be turned into sat, sat could be turned into 3 sat, all in polynomial time. So therefore clique reduces to sat in 3 sat in polynomial time, and then we finished with the proof that 3 sat can be turned into clique in given an instance of in polynomial time. Given an instance of 3 sat, we can generate in polynomial time an instance of clique, a graph G and an integer k, such that G has a clique of size k if and only if our input formula is satisfiable. All right, so we start to see that all these problems are the same. So given an instance of vertex cover, we can turn it into an incident 3 set. Given an incident of a 3 set, we can turn it into an incident independent set. So now we're going to see that this spreads a little bit wider. Okay, so we're going to go right back to the beginning of the course, and we're not going to talk about Eulerian cycles, although we could. That's not a hard problem. Remember, we saw a polynomial time solution for that, but it does reduce to sat. If you want, you can think about that after class. What I'm going to show you is that Hampath reduces to sat. Okay? So what we had was clique independent set vertex cover, and then we had sat, and obviously 3 sat reduces to sat, but what we showed was that actually sat reduces to 3 sat, and then we showed that 3 sat reduces to clique. All of these arrows mean that there's a polynomial time transformation, polynomial time reduction. Okay? So now we want to say, how does Hampath fit in here? So suppose we're given a graph G. This is very crowded. So if I'm using other software, it can be further back because I don't know why, but it zooms the screen. And then you can actually see the whole screen using the PowerShot. So the camera is running, yeah. The camera is running, the timer is running. So think about this, you're given a graph G. Now we saw on Monday that given a graph G and an integer k, you can write this formula for clique. So what about, let's just say there's a Hamiltonian path, and we don't even particularly care where it begins and ends, for example. So this is a bit of a weird Hamiltonian path. Usually you get the starting point and ending point. So how can we write this using Boolean logic, using propositional logic? Well, for each, let's have some graph like this, okay? So, can you see this? Maybe? Kind of. Yeah, okay. So I'm going to try it with black. But the black mark, I should have got new markers. Among all the other stuff, except I was messing around playing with Teams and Google Meet and Zoom. Is that better? Okay. So let's say there's A, B, C, D, E, F, G. So what we want to do, now I just made this graph up, so I don't know. I think there is, yeah, there's a Hamiltonian cycle, right? Because you can just go A, B, G, F, C, D, E. Okay? And it's not cycle, path. I don't know if there's a, yeah, I think there's also a cycle because you go B, A, F, G, E, D, no, maybe. I don't know. Okay, but it doesn't really matter. Okay, so what we're going to do, we're going to create a variable that's x, I, v. Can you read this? No. Maybe the writing is better in blue. So xiv. Okay. Okay, so I have diagrams in black, writing in blue, or maybe you can see it when I write in both. So this means that vertex V appears ith in Hamiltonian path. Okay? So we're going to have all these. So obviously every vertex has to appear somewhere. Every vertex appears only once, and you can't have two different vertices appearing in the same position. Okay? So we're going to have for how many? 1 less than or equal to I. Wait, no, that's okay. So for U, V in, so capital V is the vertex set of the graph. We have not and 1 less than or equal to I less than or equal to N. Not the case that xi u and xiv. Okay? So we add a clause that says for every I between 1 and n, and for every vertex u, u not equal to v. Okay? So I should say here u not equal to v. Okay, u not equal to v. And u not equal to v. So for every pair of vertices that are different, they don't both occur in the ith position. Okay? And then you have for I, j, well, 1 less than or equal to I, yeah, this is what I was doing, less than j, less than or equal to n, and v in v. So this is probably, this small camera can't see this anymore. We have not x, I, v, and x, j, v. Okay? And then, okay, so going over here, we have for v in v, we have either x1v or x2v or x3v or xnv. So this is just saying that for all of the vertices, they appear somewhere in the path. Right? So we're saying, I should stand in front of the microphone, we're saying that for any pair of vertices, they don't occur in the same position in the path. For any I and j, no vertex appears twice. Every vertex has to appear. Okay. What else do we have to say? Come on, it's 11:30, it's not that early. What else do we have to say to guarantee, so in these formulas to say that this is that if this formula, we take all of these restrictions and we concatenate them, we conjoin them, we put ands between them, and it's going to be equivalent to saying that this formula is going to be satisfiable if and only if this graph has a Hamiltonian path. What else do we have to say? What restrictions do we have to put on? Second condition is no vertex appears twice. Right? So if you have xiv, so xiv means that v appears ith in the Hamiltonian path. And xjv, so it says it's not the case that it's xiv and xjv for some j not equal to I. So we've got sort of the conditions, nothing appears twice, everything appears, and no two things occupy the same position. What else do we need? That would be a cycle. If we were talking about a Hamiltonian cycle, which we were talking about at the beginning, no edge appears twice would be Eulerian cycle. Well, okay, in an Eulerian cycle you cross every edge once. In a Hamiltonian cycle, yes. I'll just finish. In a Hamiltonian cycle you can't cross any edge twice, because if you did cross an edge twice you'd have to visit the same vertex. Yes, so that's what people are saying now. You have to guarantee that if I go from xiv, so from xiu to xi plus 1v, there had better be an edge between u and v. Okay? Because I want it to actually be a Hamiltonian path in this graph. So far, we haven't said anything about the actual graph. We've talked about the vertices, but we haven't talked about the edges yet. So we have to say that we go through and for I 1 less than or equal to I less than n, and v in v, if uv is not in, I know you can't read this, but it's not the camera, it's Collaborate Ultra. If uv not in the edge set, then not xiu and xi plus 1v. So we go through and we say, okay, well, it's being recorded in the high definition camera, but because the Collaborate Ultra wants this camera to be so close, this camera has to be too close so you can't see the whole board. So afterwards I'm going to go and complain to tech support that it's not my camera, it's their software. So I don't worry about it until Christian worries about it. I worried about it a little bit, but then Christian and Andrew worry about it more, and then they tell me that I should be worrying about it. But okay, we go through and we say that if there isn't this edge, then you better not be going from u to v. Okay, so we write this, all of these things, when I write this for u and v and for I, these you can say, I mean, how many pairs of edges are there? Well, n squared, how many of these? So this is like cubic, this is like cubic. So this whole formula is going to be like cubic size, right? It's going to be like O(n) to the 3. So it's polynomial. So given a graph and, well, just given the graph, I can write a formula that basically says that is satisfiable, that says there is a Hamiltonian path in this graph, and then that formula is satisfiable if and only if the graph actually has a Hamiltonian path. So here, I could go through and put an example of each of these things with this graph, and maybe the scribes will do this, saying like, okay, for U and V, so it's not the case that C is the fifth vertex and E is the fifth vertex as well. It is not the case that C is the fifth vertex and C is also the seventh vertex. Are there 7 things? 1, 2, 3, 4, 5, 6, 7, yes. It is not the case that if A is the second vertex, that G is the third vertex, because there isn't an edge. Okay, so you write this. So Ham path, I'm sorry about that. So Ham path okay, I'm just going to move 3sat. I'm going to move the label for 3sat over here. I know this is, so Ham path so in polynomial time, Ham path reduces to sat. So if we had a magic box that could solve sat, we could use it to solve Hamiltonian path. Okay? That's not super surprising. Okay? What's a bit more surprising is what I'm about to do now, which is 3sat reduces to Ham path. So this is going to be a diagram, so I'm going to use black and maybe blue sometimes for the writing. So the idea is if somebody gives us a formula in 3CNF, we want to be able to build a graph such that that graph has a Ham path if and only if the formula is satisfiable. Okay? So what formula do we want? Let's do something simple. So x1 and not x2 and this isn't or, sorry. Or x3 and not x1 or x2 or x3. So this is okay, let's yeah, okay, this is obviously stupid because I could just choose like x3 and satisfy everything. But I'm going to, do we want to do another one? Yeah, sure. And x1 or not x3 or not x4. And is that satisfiable? We can do x1 and get those two, and yeah, then we just do x3. Yeah, okay, it's satisfiable, but it's a bit more interesting because we actually have to, I don't think we can hit everything with one variable. Okay, so how are we going to do this reduction? Well, we have, just to make it easy, we're going to put a start vertex here. Okay, so we're either going to have to start or end here. And then for each clause, we're going to have a sort of a diamond. Okay, so this is going to be for clause 1. This is going to be for clause 2. And this is going to be for clause 3. And then just to make sure that it has to go from here to here, so it has to begin or end here. It has to begin or end here, right? Because once you're here, you can't go anywhere. If you start here, you can't get back. If you end here, you can't leave. So either it starts here and goes to here, or it starts here and goes to here. Everybody's happy with that? Okay. So we're going to be resetting. We're going to be starting the little camera again. Reset, start.